Okay, I think we'll get started. This is lecture 4 in the mini course on the Gibbs Phase Rule. And we're going to look now at the Gibbs Phase Rule in the context of binary systems. And we're going to investigate the concept of eutectic. So let's imagine we have two species, A and B, and we're going to mix them at a high enough temperature that we have a liquid phase. So, and we have liquid A, liquid B, we're going to mix, or A and B, we're going to mix those. We have this liquid solution, and we assume that that A and B are miscible, so they don't form two separate phases like oil and water, just one single phase. Then what we're going to do is we're going to plot temperature versus the mole fraction of A and B in that solution. And we're going to create a phase picture in that regard. So a little different than the phase diagram we saw before, which was a temperature and pressure. Now we're talking about temperature and mole fraction. Now we're going to stay in the condensed phase, so we're not going to worry about boiling some of this stuff off. So we're going to look at this liquid transitioning into a solid. And brings up some interesting ideas in general and interesting ideas in the context of the Gibbs phase rule. Okay, so let's just investigate this phase diagram. At high temperatures, we're liquid at all concentrations, so that's up in this part of the diagram. Now, let's imagine that we start at point A here, and we're going to just, let's just pick some random point in here, and we're going to drop the temperature. So our temperature will start to drop. So we'll traverse along this path. Our concentration of our solution will not change. Now we hit this point, and because there's a lot of A around, A will want to start to crash out as solid pure A. And we won't, not all of the A, but some of the A will start to crash out. And so what that will do is that it will move then the system along this line and create two phases here now, a solid A and a liquid solution. And they're connected by something called a tie line. So I've got a different illustration of that over here. At this particular temperature, we've lowered the temperature here now. This is what's happened. We've dropped to here, A starts crashing out, and so we start to produce a solution that is more favorable in terms of B. Here it was mostly A, but we start to slide here now to create more B. Now, what this tie line does is it tells us basically what's in the solution. It says, in this case, it would be solid B and this liquid solution of this particular concentration right here. So we would be able to determine the concentration based on this tie line. So here we've coming on this side, we'll continue to lower the temperature, right? That's going to drop out more and more A, and this tie line just keeps going across until we reach this very special point, this temperature called the eutectic temperature, and this point is called the eutectic point, where the solution behaves as if it's a single homogeneous, single species liquid, and it will just freeze at that concentration. And it will freeze as a solid homogeneous mixture of A and B. And that's called the eutectic. And this is called the eutectic point, and this is called the eutectic temperature. If we look at what happens to the tie line now has coalesced with this line here, and we see that we have what's called the eutectic concentration right here. So that would be X, we'll call it XE for X, the eutectic concentration or the eutectic mole fraction, and solid A in this case. Now notice, had we come from this side, we would have produced solid B, slid down this curve, which by the way is called the liquidus curve. These are called the liquidus curves. And we will end up here, but now we'll have solid B, the tie line would coalesce with this line. We'll have solid B and eutectic solution. If we drop the temperature just a little bit, then we come into this region, and under these conditions, we'll have produced solid A and solid eutectic, or the eutectic. Under these conditions, had we come from this side, we would produce solid B and the eutectic. This curve here is, another vocabulary word here, is the solidus curve. So the liquidus curves will coalesce here and intersect the, or not, will merge with the solidus curve right at the eutectic point. Now, there's a very special solution. Had we made this up perfectly, we could have started right here, right at the eutectic concentration, and as we drop the temperature, it would behave as if we were just simply freezing water, for example. It would just freeze at the eutectic temperature. There'd be no evidence of of either A or B coming out as a solid. That's the special concentration, the eutectic concentration. Okay, well, let's look at this in terms of the Gibbs phase rule, and we're going to use the condensed version here. So what that means is, instead of temperature and pressure, we're going to say pressure is basically, this is for even reasonably large pressure changes, but for modest pressure changes, under laboratory conditions, this is pressure independent. So we use the condensed version of the phase rule. And I'm going to just take and redraw this over here, and we'll look at some points on this phase diagram and apply the Gibbs phase rule. So let's look at state X here, and let's apply the phase rule. So there's two components, A and B, and then plus 1 now, which will be the temperature, minus one single phase, right? This is just the liquid phase. So we have 2 degrees of freedom, and we can kind of think about that again as putting a coordinate system on here, and our 2 degrees of freedom here will be temperature, and let's say mole fraction of B, right? If those two things are determined, then the mole fraction of A is determined. Okay, now let's come down to this line here, and or this point here. Now we have, again, A and B plus 1, but now we have 2 phases in equilibrium. We have, via this tie line, solid A and our solution, our liquid solution. And so we have only 1 degree of freedom. Now we cannot assign that degree of freedom precisely to temperature. It allows this point to slide along this curve. And so it's a linear combination of temperature and mole fraction, but it's a single independent variable. Finally, let's get to point E. And at point E, we have A and B plus 1 minus 3 things in equilibrium. What are those 3 things? Well, solid A, solid B, and then the eutectic liquid. That's what's in equilibrium here. And so that's 3. So 0 degrees of freedom. And certainly, if we change the temperature at all, we move off this point. If we change the concentration at all, we move off that point and would change the system. So visually, it looks like it should have be locked in, no degrees of freedom there. All right, then finally, let's choose just a point here down in this solid A eutectic. Here we've got 2 plus 1 minus 2 now, the solid A and the eutectic. And so that leaves 1 degree of freedom there. So it seems like it should be maybe 2 degrees of freedom, just like up here, but that eutectic concentration is locked in. Okay, so that's it for the binary systems. And so interesting application of the Gibbs phase rule. Again, we would need to go into more of the writing out the explicit thermodynamics to really dig into the details of phase equilibria for binary systems. But this is a good overview picture in terms of the Gibbs phase rule.